Okay, let us start. First, I want to ask: do you have any questions about the last time? So, uh, if now, let me remind what we did the last time at the end. So, namely, we found how to compute the so-called generating functional for the free boson. And the generating functional was 1 over z integral in dphi e2 minus 1 over 2 pi integral of dphi d bar phi d to z e2 integral g of z have z d to z. And the answer for this is up to some sign mistake, which I did the last time, the following. It's exponential of minus 1/2 integral over the whole plane, double integral over the whole plane, of such expression. Oh, sorry. Then it should be with plus sign. And as a consequence, if we want to compute a correlator of phi at 2 points, so phi of z, phi of w, equals to z minus w squared. So in this case, there is this dependence on the on some dimensional parameter r, and now let us see what is the meaning of this parameter. Namely, let us try to solve the same problem not on a sphere as it was here. It was a partition function on a sphere, or it is the same as the complex plane compactified at infinity. This difference is really essential. So let us try to compute this for the disk. So it was the first computation. Second computation, let us switch from a sphere to disk. So and to so theory lives here, and if you want to define this integral, we need to say that field on the boundary of this disk is 0. So phi at d equals to 0. So who knows what happens with the this operator with the green function of Laplace operator in this case on a plane or on a sphere. So the question is, I don't know what happens with the green function of Laplace operator if you impose such boundary conditions. So. Thanks. So it is some function that has the following properties. When z so properties of this function are the following. When z is close to w, it should have such behavior. So it's proportional to minus logarithm of z minus w. It's one property. Another property is that when absolute value of z is 1, maybe let us say that radius of this disk is some r tilde. When absolute value of z is r tilde, this g should be 0. So, did you see anything like this in some electrostatics or anywhere else? Or maybe I can just write the answer. So, and then we check that it actually satisfies these two conditions. So it equals to logarithm of so denominator is the same, and the numerator is so it should be combination. So we should basically add the image charge to the reflected point. So it will be up to some constant, which we will find now, 1 minus z bar w squared. So sorry, not this, but let us write some constant here. And now let us substitute condition that absolute value of z is r tilde. So this logarithm can be written in a different way. So like and when z lies on the circle, we can say, so when z bar z equals to r tilde squared, it equals to, so we basically express 1 over z tilde in terms of r tilde. So it equals to to cancel this, to cancel the dependence, we should say that this term is 1. So a equals to r tilde squared, and this term should also be 1, so that we have logarithm of 1, and so each of this, so a should equal to r tilde squared, c equals to 1 over r tilde squared. Yeah, maybe it should be correct. So g equals to logarithm of so here is the answer. And now let us see what happens when this circle is big, and we can consider 2 points which are close to each other but far from the boundary of the circle. So in this case, and z and it is w, and tilde is far away. In this case, this grand function behaves like a logarithm of r tilde squared over z minus w squared. So the lesson coming from this computation is the following: that this parameter in the correlation function of free boson is some scale of a system. So the system in infinite volume is defined not very well, but if we consider any system of finite volume and then send this volume to infinity, everything should be fine for expressions that have indefinite limit in this limit. So, and this is called infrared regularization, the size of the system. And this phenomenon in general is called infrared divergence, which is a signature of some large-scale correlation in the system. We say that this logarithm function is not decaying. behaves the same way for any for any scale. So, are there any questions on this? Okay. So now, so far we know this correlator, and we also know correlator with derivatives. But now let us try to study some less trivial operators. So as I said, in principle, we can take some functions of this field and call it the new operators. So let us consider, for example, the following operator, which we call the alpha of z. It will be e to the I alpha phi of z, or just such function, and try to compute the correlator. So and the question to the audience, what do you think? What kind of source J can we substitute here to get such a correlator? So what should be J of z? With what coefficients and for what points? So yes, I alpha k delta of z minus zk, right? So, and if you substitute into this formula, then we get immediately that it will be sum over sum over jk exponent sum over jk, and let us for the moment write just green function there. So let us call it a g of the w to minus 1/2 alpha gm alpha k, g of j zk. So in principle, this equation, this expression looks fine until we start thinking what are these g's, because well, so we know that it is symmetric. So we can reduce the summation to summation over j less than k. So the first term is nice. So it's sum over j less than k. But the second term is not so nice, because it looks like this. So it's 1/2 of sum over k alpha k squared g of zk zk. And if you look who this g is, we see that it is a logarithm of 0. which is not very well defined. And this is this phenomenon called normalization, where realized that some quantities are naively infinite, but it can be redefined so that resulting quantities behave nicely. And this is done in the following way. So, okay, this function naively is infinite, but let us say that our theory contains some regularization. For example, we consider some theory on a lattice where any correlators are definite and are finite. Or we consider some cutoff in the space of Fourier modes of this phi. So we find some way to construct a theory which approximates our theory on large scales, but is finite on the small scale. And this means literally that we say that this Green function computed at the coinciding points equal to some number, to some finite number, where this small r is called ultraviolet cutoff. And this big R, as we know, is called infrared cutoff. So we assign this value to this function, and this R should go to 0 in the limit. So R goes to 0, big R goes to infinity. So having this, we can write the answer. So let us write separately the part which depends on infrared cutoff. It will be this expression. Then there will be a product of over alpha j alpha k for j less than k. And there will be this product depending on the UV cutoff. So and now about this logic of renormalization. You see that correlator of this fields is proportional to, well, let us write here question marks sign, or let us add some experimentation saying that it is initial operator. So this product is proportional to this correlator is proportional to a product of something that depends only on k. Which means that if we now introduce the field v of alpha k of z equals to R2 minus alpha k times v alpha k 0 of z. And the correlator of such fields will be finite and are independent. So uh, so it was the first thing. And by the way, uh, I don't know what was the dimension, in a sense, physical dimension of the original field phi. So this phi. So if I measure it, for example, in electron volts or something or some other energy unit, what will be the power of this of this energy scale? Mm-hmm. Because action and in general any expression which is in the exponential has dimension 0. D bar and d to z cancel each other. So the only option is to have dimension 0. And the same applies to this original exponential. So the dimension of original exponential is also convolves to power 0. And what is the dimensional of renormalized field? Some physical dimension. Hmm? Oh, yes. Mm-hmm. Thanks. Oh, sorry, I missed here squared. It is important because it was alpha k squared. So it is electron volts to alpha k squared. So it was some physical kind of physical argument showing that the field which was naively dimensionless acquires some dimension in the quantum field theory. And such dimensions are called anomalous dimensions, in a sense that they appear from, I don't know if it is correct to call this conformal anomaly, and don't know precise etymology of this name, but this is the name for dimension which is generated by quantum effects. Sometimes it happened that we have some fields that had some classical dimensions, and then they receive quantum corrections. But in this case, everything is quantum. So it's Okay, and let us look what are the implications of this fact for the correlators of such fields. Namely, let us compute the correlator of V alpha of Z V minus alpha of W. So according to this formula, it will equal to 1 over Z minus W to 2 alpha squared. And some a reminder. The last time we saw that Bergman bidifferential dz in dw over z minus w squared is conformally invariant. Under the global transformations. So it means that if we now multiply this d alpha, this v alpha and v minus alpha by power of dz dw, we will get a power of this Bergman bidifferential. So namely, we can write here dz to power alpha squared v alpha of z dw to power alpha squared, and it will equal to dz dw over z minus w squared to power alpha squared. So it is also conform. Oh, sorry, I missed the field. So we can conclude that such expression dz alpha squared times v alpha of z, which can be written equivalently like alpha squared over 2 dz bar to alpha squared over 2 v alpha of z is conformally invariant. So which means that from the differential geometry point of view, this v alpha of z is a coefficient in the fractional differential form of weight alpha squared over 2 and alpha squared over 2. And these weights are called conformal dimensions, homomorphic and anti-homomorphic dimension in a sense. So the notation is the following: it is delta and delta bar, homomorphic dimension. and a physical dimension is a sum of delta and delta bar. And there is also another quantity which is called spin. It equals to delta minus delta bar. The meaning of it is the following. So if we have a field with spin 0, like in this case, it is invariant under rotations of the plane. We don't need to multiply it by anything. But if the difference of the dimensions is different from 0, rotation of the plane will give some prefactor, dependent precisely on this difference. And there are examples of such scalar fields and also fields with spin. So in particular, if we want to get not very fairly, but almost fairly, filled with arbitrary spin, we can, in principle, formally decompose this operator the alpha of z into the product of two. So later we'll understand what is the meaning of this factorization at the operator level. So, but now we can say that it's just formally. So this factorization follows from the observation that this correlator can be factorized into a product of z minus z times z bar minus z bar. So if something happens at the level of all correlators of such fields, we can hope that the same happens at the level of operators themselves. And in general, it is standard logic in CFT and in any other quantum field theory that if some equality holds in any correlator with any set of other fields, then this equality by definition holds at the level of operators. So if we work only with exponential fields, and actually these fields are also fine because they can be obtained by differentiations of these exponentials. So we can say that there is this homomorphic times anti-homomorphic factorization, and correlators are defined precisely by two factors in this formula for z's and for z bars. So, are there any questions about this? Mm-hmm. So, alpha here would be a real number. Yes.
then in the dz squared, dz alpha squared d alpha, we get dz wedge dz times dz bar wedge dz bar.
It's not wedge.
It's not wedge.
It is symmetric. No, well, not symmetric, just tensor product.
So and also it's like, so it's not really a differential form.
How how to call well, so we can say that this value of z bar dz alpha 2 over 2 dz bar of is in so it's a fractional tensor powers of such vector bundles, and they're defined because these are one-dimensional vector bundles or line bundles. In the sense that we can compute a dz to arbitrary power a of a vector, and it will be by definition dz of a vector to power a. So there could be some problem if we had a higher dimensional vector space, because in this case it would not be clear, for example, how to take fractional power of dx plus dy. But since everything is one-dimensional, we say that this these are just forms of degree a. So, like we can say that in the so like we have quadratic forms, not bilinear forms, but quadratic forms, and in this case we have adic forms. Or adic. Oh, sorry, yes. And if we don't put star, it will be just the inverse bundle. So T1 0 star M tensor T 1 0 M will be just functions on M. So this line bundle is inverse to this, and this is one of the consequences of the fact that we work in two dimensions. So we not only have infinite dimensional symmetry algebra, we also have some interesting representations. Because in higher dimensions, we can only have non-integer dimensions of field, but for example, no non-integer or non-half integer spins. And here everything is possible. So, are there any other questions? So, but it's not all about this formula for this correlator, because we have already get rid of this ultraviolet divergence, but infrared divergence is still there, and its effect is different because remember that this R should go to infinity. So R to integral of sum of minus alpha I squared has two options. So if sum of alphas is different from 0, it goes to 0. And when sum of alphas is 0, it is just 1. And this is called one charge conservation, and I will understand later the meaning of this condition. Oh, maybe actually we can understand it now. So U1 charge conservation. So keeping this in mind, we can write the formula for correlators of this halves, homomorphic and anti-homomorphic halves of this field. So correlator of V alpha 1 of Z1, V alpha n of Zn will equal to 0 when sum of alphas is different from 0, and the product over I less than j, V alpha I of Zi, sorry, what I'm writing, Zi minus J to alpha I alpha j. Yes, because R is such number that should be sent to infinity at any possible moment, because it is some infrared regularization. So it is something that is supposed to be infinite from the very beginning. Because if we want to study the actual theory with a boundary when R is finite, we should do something like this, or choose some other infrared regularization, like put it on a torus or on some other domain. And the answer in this cases will not be so simple as this logarithm. So it is really the formula for the limit R to infinity. So is it clear? Like, Okay, it's a universal. It will be the same for any regularization. So we'll have just one number which is insensitive to the shape of boundary far away. And the same situation is with this ultraviolet regularization. It does not know about the concrete theory. It only knows a single number. This number which is needed to define a correlator at coincident points. So, by the way, concerning this R, uh, I can probably show you one example of, well, let me maybe keep this formula. This one. So one possible way is to say that this theory is defined on a lattice, maybe even on a finite lattice. So in this case, gain function will be something of this kind, sum over e to the I kx over cosine of kx plus cosine of ky minus 2, sum over k different from 0. So it will be finite when x is 0. Another regularization is a momentum cutoff. So we had a formula for this g of x, which was schematically the integral of ik x d to k over k squared. And this integral was actually divergent both at a large case and at a small case. But so we should actually write something like a integral from 1 over R0 to 1 over 1 over a big R to 1 over a small r. So this divergence at small case is related to divergence at larger momenta. And and we also see that this order is the same for any x because it does not depend on x, and we see it from the formula for the correlator for this gain function. Or probably I erased it, but this formula always contained a big R, and this upper cutoff becomes important when we put x equals to 0. Otherwise, it can be neglected. So when people think about some regularized theory in QFT, they almost always think about momentum space with some ball of size lambda. And probably something can also be removed from 0, but it is different phenomenon. So it is, for example, not responsible for this normalization. So it's something at the big scale. Okay, so is it fine? But now let us try to understand this phenomenon. Why does it happen that our correlator vanishes when some condition on alpha is not satisfied? Like, how could we see it from the very beginning? So this topic is called symmetries of classical and quantum theories. Let me change my color. So look at this action. We see that if we shift phi by constant, it will not change. So S of phi plus C equals to S of phi. And now let us use this transformation in the integral we have, which computes our correlator. So this correlator V of alpha 1 of Z1, V of alpha n of Zn, equals to the integral of in d phi e to minus s of phi right. So since we're integrating over all fields, this measure should be invariant under this symmetry. So for such simple symmetry, it is the natural assumption, but in principle, it can happen that measuring the path integral is not invariant, and this is called anomaly. And so the usual anomaly, which appears in almost any theory, is a scale anomaly, but there are also anomalies related to gauge symmetries, which also appear quite often. But in this case, it is just an integral of fields in any point, and we just shifted by constant. So integral from 0 to infinity should not depend on this. And so we can write that this correlator is again d phi e2 minus s of phi plus c, which is the same as s of phi divided by z, and here we have e to e alpha 1 c plus phi of z1 and so on. So action is invariant, fields are not invariant. So it equals to correlator of e to I alpha 1 c v alpha 1 of z1 and other fields. So in general, it equals to e to I sum of alphas times c times the original correlator. But we started from this correlator, and we know that this two quantities should be equal. So it tells us that it tells us that 1 minus e to I c sum of all phi's times the correlator of v alpha 1 v alpha n is equal to 0. And so we come to this conclusion that if sum of alpha is not 0, then this correlator is 0. So we cover this. And this is a phenomenon of the same kind as the such kind of formula, because here we were able to recover this correlator from recover this condition on the correlator from such a symmetry of the theory. But actually, this formula could also be obtained just from global conformal symmetry, because the only a form of such a weight which is invariant on the conformal transformations in this Bergman bidifferential to appropriate power. So we could obtain it without this computations with the path integral and so on. So it is a universal expression for any conformal field theory. And such condition is also universal for any theory which has U1 symmetry. So if some global symmetry is not satisfied, if the sum of charges corresponding to the symmetry is non-zero, then correlator should vanish. So what do you mean by compact? No, because it is some jargon. People usually think about algebra, but here you're right, it is not compact. But as far as I know, uh, people don't call it R symmetry. So maybe more appropriate name is translation symmetry, but it's kind of target translation because phi is a map to some one-dimensional space similar to the space-time in the string theory. Yeah. Hmm? Because if you don't take it, and for example, let us think that this IR cutoff is realized as as a boundary condition on disk. Like phi is 0, then a boundary condition is not invariant under the symmetry, and there should be no charge conservation. So, in some sense, this conservation appears automatically because of the mirror charges. So structurally it looks like this. Okay. Any other questions? So, but, now uh, let us think about another thing. About conserved quantities. So probably you heard somewhere in classical mechanics that if a theory has some symmetry, then if some mechanical system has some symmetry, then there should be some conserved quantity corresponding to this symmetry. And what is the example of this quantity corresponding to this shift? Let me just write some expression and check that it is conserved. And then I will explain why it is why it corresponds precisely to this symmetry. So let us define G mu. G mu is d. Let us use some other letter, big G, because we have G source. And since equations of motion are d mu phi equals to 0, therefore d mu of g mu equals to 0. Actually, there is another funny conserved charge in this theory, because for this charge we need equations of motion, but we also have topological current G mu topological is epsilon mu d mu phi, and this is conserved just by the definition. And so the meaning of this charge is the following. So first, there are these currents, and the question is what are the corresponding charges. So this Q corresponding to J is the integral over the space of zero component of this charge. Dx J zero of t and x, and this charge is so it is integral in dx so let me think. No, sorry. Yeah, it's for different. It's for different charge. So there is such expression, and we can check that it is conserved. So it's integral for t for time equals to constant. So. So the argument for this charge conservation is simple. I just take the integral over such a strip, like for T1 and T2. So let us take this domain D and take the integral over D of d mu j mu d2x. So it will be 0 because charges conserved, but on the other side it will be the difference between the integrals t equals to t2, 0 equals dx j0 minus integral over t equals to t1 dx j0. Like this. So it's kind of a standard argument why this condition means a charge conservation. So this charge and this topological charge q j top in the integral in dx of so this time squared integral of dx phi. So it will be just the difference of phi of plus infinity minus phi of minus infinity. So that's why it's called topological. So are there any questions about this? So now the question is, it's the original question, how to relate conserved charges to symmetries of our theory. So, and the answer to this question is called the Noether theorem. So, mm, so suppose that we have some infinitesimal symmetry of the action. So S of phi plus let us call this symmetry operator some G. So this G hat acting on phi is a single object which may be complicated. So it can contain derivatives, constant shifts, and so on. Multiplication by something. But suppose that we have such symmetry that it preserves the action up to terms of order epsilon squared. So there is symmetry. So we see that this statement is formulated in such a way that we take our action and perform some small variation with its argument, but this small variation is of some particular type. It is given by this symmetry. And the question is, where else can we see such kind of phenomenon when we perform some variation of the action and it is preserved? So another place where we see it is the derivation of equation of motions. Namely, the statement is that if phi satisfies the equations of motion, well, maybe we can say, if and only if. So if phi satisfies then, so if and only if S of phi plus epsilon delta phi equals to for any delta phi equals to S of phi plus O of epsilon squared. So this statement is similar, but with extra condition that equations of motion should be satisfied. And actually, this is something that we need because to have a charge conservation, we need to use equations of motion in almost all cases. And these topological charges are some exception, and maybe they can be obtained from some variation of the Noether theorem, but I even don't think how to do this. So the normal charges definitely need equations of motion. So it suggests that we should first study something at equations of motion. And let us just try to combine these two statements. Namely, let us consider a special form of variation of the action, which is obtained from this formula. So.
I have a question.
Hmm?
What's the difference between G hat and delta?
Because delta is arbitrary. So equations of motion satisfied by phi, like these equations, are equivalent to the statement that variation is zero for any delta phi. Because let us just write how it looks like in this particular case.
But I see the second. Okay, these are two conditions that do both need to be satisfied in order for not to be able to be equal.
No, could you say it again?
So these are two conditions that you like. These two hypotheses of Noether theorem.
No, it's not a theorem yet. It is just so this one is a definition of what we call continuous symmetry, and this is just a statement a statement about equations of motion, like and.
I don't see ever G hat applied anywhere in the second statement.
But we don't need it. It is just the general setting of classical mechanics, that any system is described by the classical action, and equations of motion of this system are obtained from the statement that variation of action is zero for any delta phi. So let us just see how it works in this case. So here we have s of phi, which equals to 1 over 2 pi integral of d, maybe 1 over 8 pi d mu phi d to x s of phi plus epsilon delta phi up to the second order in this epsilon will equal to 1 over 4 pi integral of d mu phi d mu delta phi. Plus original action. So is it clear? So now we integrate by parts. So s of phi plus epsilon delta phi minus s of phi equals to minus epsilon over 4 pi integral d mu phi delta phi due to x plus O of epsilon squared. And to get equations of motion, we say that this equals to 0 for any delta phi. So S of phi plus delta phi minus S of phi is of order epsilon squared is equivalent to the statement that d mu phi equals to 0. So it's how classical mechanics works. For example, if you want to study the motion of a particle in the field U of x, we need to construct the action which depends on x of t, and it is the difference between kinetic and potential energy. And the variation of this action is integral of minus mx 2 dots delta x minus v prime of x delta x. So statement that plus s of x. So statement that it is 0 for any delta x. So is equivalent to the second Newton's law for this potential. And here we have the same with the difference that and now we have more coordinates, or we can say that the system is infinite dimensional in the sense that space coordinate is an index of the dynamical variable. So we have time evolution of the profile of phi, and it's described by this equation. So potential. So if we want to separate kinetic and potential part, in this case, then a potential will be minus plus and minus. Well, to get the actual classical mechanics, we need to consider Minkowski signature, and in this case, energy will now be a function of phi, and it will be a gradient of phi squared. So v of phi is the integral of over dx dx of phi squared. So it's potential part of the action. Okay, so I understand that this condition that variation of direction for any phi vanishes is equivalent to equations of motion. So it's how the classical mechanics is constructed. And by the way, if we think about relation between classical and quantum mechanics, it is especially transparent in this path integral formalism, because in classical mechanics this restriction principle comes from nowhere. It is just postulated. But if we switch to quantum mechanics or to quantum field theory, then another quantity is postulated, namely this path integral. And if you want to compute this path integral, you can compute it by the saddle point approximation, because usually the Planck constant, which you neglect, enters here. So in the limit, when Planck constant goes to 0, the leading contribution to this integral comes from the saddle point, which is precisely defined by condition delta s equals to 0. So, are there any questions about this? Okay, so but let's go back to this construction. So we have another setting. This infinitesimal symmetry, and let us try to modify this symmetry so that it stops becoming the actual symmetry. So let us consider the transformation as phi plus epsilon of x g hat acting on phi. Let me first say that okay, let us consider such a quantity. So this transformation is not a symmetry. Let us consider this difference and call it well, let us say that this can be expressed as some function that depends on phi, on everything, integral due to x, some function times epsilon of x plus O of epsilon squared. This is possible because the actions usually are some polynomial functions of phi and of its derivatives. So in any case, we can first expand everything in this epsilon to the first order, and then if we get some derivatives of epsilon, we just integrate them by parts until we get just epsilon alone. So let us write that this f depends on phi, d phi, and so on, and epsilon. So now, what what do we know about this expression? So the first fact we know comes from this I don't know how to call it, main statement of classical mechanics, that if phi satisfies equations of motion, then any variations of the action are zero. If then this integral of in d2x f times epsilon of x equals to 0 for any epsilon. Therefore, this f of phi d phi so on equals to 0 if so like, vanishing of this function f is a consequence of equations of motion. In other words, so here we use the first the second statement. And now let us use the first one. So now let us suppose that instead of this, epsilon of x is a constant. In this case, we recover the situation when this modified symmetry becomes the actual original symmetry. And since it is symmetry, it is symmetry of the action, which does not know about equations of motion. So this variation of the action should hold for any phi. So now we have statement not for any epsilon, but for any phi, and the statement is that the integral of d2x f of phi d phi and so on. So equals to 0. So it is some differential polynomial of phi, and the only possibility for it to vanish for any phi is to be a total derivative of something. So so that it vanishes because of the integration from minus infinity to plus infinity. So this f of phi, d phi, and so on equals to sum from I equals 1 to d. Well, in two-dimensional space, d is equal to 2, but it will be some dxi of j I of phi, d phi, and so on. So, in other words, we can say that this f equals to, I forgot with which sign, probably with minus sign. It should equal to minus d mu j mu. So to be precise, it's a statement about existence. So it states that there is some vector gmu, that this f appearing in this variation is minus its divergence. So if we now integrate this this integral by parts, it can be written in the following way. So s of phi plus epsilon epsilon of x g hat phi minus s of phi equals to the integral d to x sorry, what did I write? Equals to integral g mu d mu epsilon. So now we see that if we are on the equations of motion, this integral will vanish because d mu equals to 0. When we are when epsilon is constant and we take the actual symmetry, it vanishes because d mu epsilon is 0. So you see that a consequence of these 2 points is that so I can rephrase it and rewrite it once again. So if phi solves equations of motion, then d mu j mu is equal to 0. And it's a statement of Noether theorem that continuous symmetries give rise to conserved quantities. So, and this proof of Noether theorem gives us some explicit recipe how to obtain such conserved quantities. Namely, we should take the actual symmetry of the action, make it coordinate dependent, and integrate everything by parts until we get d mu epsilon times something, and this something will be our conserved current. So is it fine? Is the logic clear? Are there any questions? Maybe you can try to think about this a little bit more, but I don't I remember other proof of Noether's theorem, and I like this one very much because it is absolutely agnostic to the form of theory, and it can provide you this conserved charge in any situation. So mm, you just you need to be able to integrate by parts and to cancel terms that should actually cancel. Okay, so let us now apply this Noether theorem to derive this conserved current, which was written somewhere, to derive this dmu phi. Oh, probably erase this. Actually, I don't need to erase everything. Because here we see this this formula for the variation of action. Let me erase maybe this. Okay, so we see this variation of action, and let us modify it a little bit. Let us say that this d phi is equal to dot phi equals to epsilon g hat phi. Here we will have so epsilon of x. So if g hat phi equals to a constant, let us say that it equals to 1. And this is just the usual variation. So g mu epsilon g mu. Here it is super easy, right? Are there any questions about this? But now let us try to consider a more complicated transformation. So, you can, in principle, do the following. You can take phi of x mu and shift it by some vector a mu. And this will be a symmetry, right? So if you want to write it in this infinitesimal form, we can write that phi of x mu plus a mu is phi of x plus a mu d mu phi plus and so on. So infinitesimal transformation is this. D hat phi. But now let us consider the transformation where d hat phi is with a mu depending on x. And substitute it to the action. It will be the same formula. 1 over 4 pi. So now we will have two terms. One term is derivative of a nu, which is fine, which is already a derivative, and another term will be with derivative of phi. So if you want to do something with the last term, we need to notice that it is a derivative of d mu phi over 2. So this integral can be written as 1 over 4 pi to go no, d mu phi squared. Maybe better to say d mu phi over 2. So finally we can integrate the last term by parts and get 1 over 4 pi integral of d to x d mu a nu like this. And this second factor is called energy momentum tensor. very important quantity in quantum field theory and in conformal field theory in particular. So the statement is that so we see that it is symmetric from this formula, and the statement is that it is a conserved tensor in the sense that d mu d mu nu equals to 0. So this is the set of conserved charges that correspond to space translations. And uh, because of this, they have two indices. One index is the current index. Another index corresponds to this space translations. But it turns out to be symmetric, and we will understand later what is the origin of this symmetry. Why we can choose it always or no, almost always, maybe, except for some pathological cases, which I don't actually remember. Okay, so are there any questions about this? So, and of course, the exercise is to check that this conservation law actually holds. And it's also interesting to look at different components of this energy momentum tensor, which have meanings of energy density, momentum density, momentum flow, energy flow. So it makes sense to write it in components. And also, there is an important exercise which we will do, but it is better if you also try to do it at home to compute this energy momentum tensor in these coordinates. So we can use not x1, x2, or x and y. We can use homomorphic and anti-homomorphic coordinates. So please try to compute these quantities, maybe just to have something to compute to understand how everything works. Okay, so that's all for today. Thanks for your attention.